You'll have an exam on Friday, right? Okay. And so what did I say? So I posted the practice exam for the more like the one Lee will probably give you because it's based on the exam he gave a couple quarters ago. For Varn, I was hoping he would post something like he did last time about like because last time he posted what like a list of the content you're responsible for. What's that? Yeah, he hasn't posted anything yet. I will try to get something written for him more specifically by Wednesday. Yeah, I mean, I can make something up. It shouldn't be too hard to do. And then, and just as a clarification, did either of your instructors say that the stuff in chapter 12 was going to be on this exam or not? 12.1? Okay, nothing for after that? Okay. All right. Good to know. Well, that said, let's start talking about section 12.1. 12.1, which sounds like an innocuous idea here, principles of counting, right? How hard could it be to count stuff? Well, it can be challenging. There's a few rules we'll kind of talk about, but a lot of these problems I will point out, or a lot of these ideas, really kind of are based on reading well, right? You have to read the thing well, understand kind of what's actually being asked to then be able to even answer or think about how to answer the question. And I'll just say a general kind of statement, which is mostly true, which is that when you read the word and, so like this and this happen, we typically multiply those things together. And we'll say more about that as we go on. Whereas when you read the word or this happens, it usually means we are adding things together. That's not like a hard and fast rule, but it's pretty generally true. So I'll just point out that and typically equates to multiplication and or typically equates to addition. We will say more about that as we go on. Let's look at some examples here. So here's a very kind of made up example. Planning your fall quarter schedule for next year. And we're going to make up some things that don't really feel true, but that's all right. And here's what we're going to do. We're going to take a stats class, a bio class, a chemistry class, and a music class. And there's 4 different stats sections to choose from. There's 2 bio sections. There's 3 chemistry sections. And there are 2 music sections. Assuming none of the classes overlap in any ways that make it impossible to do so, how many different schedules could we come up with? I will say this definitely underrepresents how difficult scheduling problems really are. Scheduling things in reality is much more difficult than just pick one of these, pick one of these, pick one of these, pick one of these. But we're going to make it easy. So here's the idea. We essentially have choices at every juncture. So first we have to choose one of the stats classes. So we're going to choose section 1. We'll talk about the rest of the section. Or section 2 or section 3 or section 4. And then for the first section, well, we can either choose the first biosection or the second biosection. Same deal for the rest. I'm not going to write this for all of them because it's going to get kind of repetitive. And then for each biosection, or I should say for each combination of a stat section and a biosection, we can pick one of the three chemistry sections. And then for each chemistry section and bio and stat section choice, we can choose one of the two music sections. So we could draw this kind of diagram for for each four of these, we'd have, two biosections, and then for each bio, you could have three chemistry choices. And then for each chemistry choice, you could have two music choices. And at the end of the day, I like to think of these as a bunch of different paths, different paths to get you a different combination every time. You could have stats 1, bio 1, chem 1, M1, or stats 1, bio 1, chem 1, M2, or stats 1, bio 1, chem 2, M, right? You can just go on and on and on and on. And so the way we're going to get here is we want a stats and a bio and a chem and a music section. So we're going to multiply those numbers together to get the total number of choices, the total number of schedules, bless you, is going to be 4 times 2 times 3 times 2. I know the order doesn't really matter, but trying to keep things in order here. So that's some number, what, 48, I think? So 48 different schedules we can make under this setup. It's kind of it. So really, the first kind of rule of thumb or rule of counting is when you're trying to find out how many different ways you can do a bunch of different things together, you end up multiplying all your options together. We have 4 choices for stats times 2 choices for bio times 3 choices for chemistry times 2 choices for music, and that's kind of it. Let's look at another example. So yeah. So we're trying to make a study, and a study of the effects of light and fertilizer levels on plant growth. Welcome. 1 second. We plan to study 5 different fertilizers and 3 different light levels. We also don't just want one plant for each combination because that one plant we picked might not be great, right? You kind of sometimes plants just do different things. So we're going to have for each combination of fertilizer and light, we plan to have 4. The word we use here is replicates. I would just call them plants. Whatever. So how many plants do we need? Well, I think we need 5 times 3 times 4. 5 different fertilizers, 3 different light levels, 4 plants at each level. You could draw a little picture here. Like say, like I have 5 different fertilizers. So fertilizer 1, 2, 3, 4, and 5. And then that's at light level 1. And then we could have another 5 different fertilizers at light level 2, and another 5 different fertilizers at light level 3. So there's 15 different possible combinations of fertilizer type and light level. And then for each 15 types of fertilizer and light, we need 4 plants. So 4 times 15 is going to give us 60. Again, not really a lot more to say here, other than we're multiplying a bunch of numbers together. Not super exciting. It does get more interesting. So I think that's called the multiplication principle. I've just never really giving it words, but that's, I think, the name of it. Let's move on to more interesting things, unless there's questions about this. The bigger concepts, I think, are the ideas of permutations versus combinations. So, permutations are the number of arrangements or orderings of some number of items. The thing to remember with permutations is order matters. We care about me being first, you being second, you being third versus you being first, you being third, me being second, right? That's a different permutation of the three of us. So order matters. So some examples. So let's say we're at the library studying math. We decide to walk around and look at the books for a minute, and we see on the shelf four different math books, five different chemistry books, and six different biology books. How many different ways can we arrange? Wow, that's a can. We arrange the 15 books on the shelf. Well, when I'm answering a question like this, I typically think about having 15 spaces. So there's 15 spots the books can go in. 15 is kind of a lot, but we'll 5, 6, 7, 8, 9, 10, 11, 12, 15. So there's 15 books and there's 15 spots. And if I had, well, no, it's not worth it. So really the question to now ask myself is, how many choices do I have for the first book I'm going to put down? Well, how many books are there? 15. So I have 15 books to choose from. So there are 15 different first books I could put on the leftmost spot on the shelf. And then after I've chosen one of those books, for the next spot, how many choices do I have? 14. And then for the next spot, 13, and so on and so on and so on, times 12, times 11, all the way down to times 3, times 2, times 1. We don't want to write all that. It becomes a pain. So there's a notation for this when you have a number multiplied by every integer all the way down to 1, and that notation is the factorial notation. So we have 15 factorial ways of arranging these books. And more to the point, when we say n factorial, that just means that number n has to be a positive has to be a non-negative integer, and that number is multiplied by every number less than it all the way down to 1. So n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So if I say 7 factorial, you should be thinking, okay, he means 7 times 6 times 5 times 4 times 3 times 2 times 1. Also, one other thing that is a little bit important, which is kind of funky, I'm not really going to explain it right now, but I'll tell you that so let me ask you a question. What's 5 to the 0th power? 1. And it's defined to be that because, well, really because of the additive law of exponents, because it has to work that way. Well, in a similar way, there is a rule, which we'll talk about a little bit later, that's defined in such a way that we have to have that 0 factorial is also defined to be equal to 1. It doesn't meet right, it's not the same. Like 1 factorial is 1 because it's 1, that's it, right? 2 factorial is 2 times 1 is 2. 3 factorial is 3 times 2 times 1 is 6. But we just defined 0 factorial to be 1 because we need it to be so some other properties work the way they're supposed to later. Don't sweat it too much. Back to this example, what if we asked instead, how many ways can you arrange the books so that books of the same subject are next to each other? Or a better word, books of the same subject are adjacent. So sometimes you're doing a problem like this, you just have to kind of make something up and then kind of fix it later. So we don't know which books are first, but we'll just choose one of them to be first. So we'll say, let's put the math books first. So if the math books go first, well, there's four different math books. So there's four choices for the first book. There's three choices for the second book, two for the third, one for the fourth. And then let's say we have chemistry next. So the math books, for the chemistry books, instead of writing it all out, well, there's five different chemistry books, so there's five factorial ways we can arrange those five books. So they're still all next to each other. And then for the biology books, since there's six of them, there's going to be 6 times 5 times 4 times 3 times 2 times 1, or 6 factorial ways of ordering those 6 books, so they're all still next to each other. And then we also have to think about, well, we didn't have to put math first, chem second, bio third. We could have put math first, bio second, chem third, or chem first, bio math, or chem first, math bio, or bio first, math chem, or bio first, chem math. So there's 1, 2, 3 factorial ways of arranging the subjects. So we have to multiply by 3 factorial. This is the number of permutations, orderings, arrangements of the subjects, math, chem, and bio. So that's our final answer. 4 factorial times 5 factorial times 6 factorial times 3 factorial. If the number is small enough, you should find it. If the number is not, you should just leave it like this. This, I wouldn't bother doing anything else with, even though I know that that's 24, that's 120, that's 720, and that's 6. I don't want to multiply that all out. Leaving it like this shows that you know what's going on. You don't need to write the final. And I believe, for those of you in Varn's class, I believe web work takes the factorial notation just fine. So if you're writing out something like this, don't bother finding 10 factorial. Like just type 10 exclamation point. And that is the answer, if that's the answer. Yeah, okay. Let's see, what else here? Yes, so let's look at a few other examples here. How many ways can we arrange the letters in the word math? And I should say, I'm going to be a little more explicit here. How many different ways? It doesn't really change anything for this problem, but it will for the next problem, or at least it'll make it more clear what's going on. So in this case, I'll also point out when people ask this kind of question, they ask how many different words you can make. A word is not like a real word that you could find in the dictionary. HAMT is a word as far as this problem is concerned. So words, when you're just rearranging letters, mean just a way you could arrange the letters. It doesn't have to make up a real English word. So we could have anything, right? You could have A first, M second, T third, H fourth, and so on and so forth, right? You could do all sorts of things. Why am I writing all these out? Good question. Why am I writing all these out? Just to kind of show you how I think about writing the permutations if I actually had to. So you can kind of see here, I keep things as far left constant for as long as I can. So that A is always first, and then M is next until it can't be. I have AMTH, AMHT, and that's the only way I can have A then M. Then I switch what's second. I have AH and then TM and MT. And then I switch what's second. I have AM, TH, and HT. And then I could get the same number of permutations if I did M first and 3 things after it, or T first and 3 things after it, or H first and 3 things after it. So there's going to be exactly 4 factorial ways of rearranging these 4 letters to get a different word every time. A different word every time. And you kind of see here, right? It's kind of also showing why it's working that way, right? I have 4 choices for the first thing, 3 choices for the second thing, two choices for the third thing. And once you've done the first three things, you have no choices left. You have one choice. One choice really is no choice, but okay. So that's a little bit kind of seeing why it's working this way, why it's really four things there, right? One, two, three, four, and then three things here, and then two things here, and then one thing there. However, this is kind of a unique situation because all the letters are different. So what if we asked the same question, but now we asked how many different ways can we arrange the letters in the word data? Number of different ways to arrange the letters in data. And the problem here is that you have two of the same letter. And so even though we're going to, for a moment, consider those different, we're actually going to write these all out. You don't have to write these all out, but I'm going to write them all out. So let's say we have data and that first A is A1 and that second A is A2. So I'm going to start with, yeah, A1, A2, TD. And then A2, nope, that's not the way I do this. A1, A2, DT, A1, D, A2, T, A1, D, T, A2, A1, T, A2D, A1, T, D, A2. It gets a bit tedious, right? You're like, yes. I'm like, oh my God, we're going to do this how many more times? So I want to point out for the next one I do, they're all going to be the same, meaning I'm going to put A2 versus of A1. So I'm going to do A1, A2, TD, and the same for these. This is going to be A1, A2, DT, A1, I said I was going to do them backwards and I didn't. Apologies. A2, A1, A2, A1. A2 is first, not A1. A2D, A1T, A2D, T, A1, A2T, A1, D, A2, T, D, A1. All of these are the same as each other, right? If you ignore the subscript on the A, these are the same, these are the same, these are the same, and so on and so forth, all the way down to here. And then for the other ones that I'm not going to write out, but like, we could have TD, A1, A2, and so on and so forth. You're exactly going to double those up as well. So of your total 24 things, half of them are just a repeat of the other half. So really, the total number of ways is going to equal 4 factorial, the number of ways of rearranging these four letters, divided by 2 factorial, the number of ways you can interchange the letters that are the same as each other. So this 4 factorial is the number of ways of arranging the 4 letters. And this 2 factorial is the number of ways of arranging the 2 A's. So when we have these repeats here, we have to divide by the number of ways of permuting the repeated letters so that we don't overcount, so that we don't think of, none of these are really words, so that we don't think of the word AATD as the same as different as the word AATD, right? They're still the same combination or permutation of those letters, right? This is just AATD, this is AATD. So they're the same, they just look a little different in that context. So then we can ask questions about more interesting words like, I don't know, statistics. How many letters are in statistics? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10? Yes. Did I spell it right? Yes. Okay. Does it need to be spelled right? No. Okay. So we're going to start off by saying the number of ways, I always forget to say the word different, the number of different ways to permute these letters. Okay, well, there's 10 factorial ways of rearranging all of them. But how many T's are there? There's 3 T's, so I have to divide by 3 factorial. And are there any other letters repeated? I, yep, there's 2 I's. So I got to divide by 2 factorial. Any other letters? S. I have to divide by 2 factorial also. I think those are all the repeats because then I have an A, Oh, no, there's three S's. I missed one. Statistics. And then there's an A and a C, which you could divide by a 1 factorial and a 1 factorial if you wanted to. It's not going to change anything. I will point out, though, if you did that, it would make it really, really clear that all the things in the bottom have to add up to the thing in the top. So the 3, the 2, the 3, and the 1 and the 1 add up to 10, which is the thing on the top. So it's kind of a nice way of seeing that there's some kind of pattern here. So let me ask you all to do the following one. See if I can actually write this. The number of different ways to permute the letters in Mississippi, which if you've never heard it before, it's MISSISSIPPI. I'm pretty sure there's 4, 8, 11 letters in there. Go for it. I know. Super exciting. Yeah. We're going to talk about one of my favorite functions in a second, which is kind of cool. We got time. That's not the tens form I'm thinking about it. So with this problem, we should get 11 factorial on top. Let's see, there's 4 S's, so we have to divide by a 4 factorial. There's 4 I's, so we divide by another 4 factorial, and there's 2 P's, so a 2 factorial. And if you wanted to, we could throw in a 1 factorial, even though it's not at all necessary. Yeah. Okay, one more example. And I do actually want to calculate this next one. So here you could calculate this, but it's kind of annoying, right? I don't really want to write it out. But sometimes, like in this next example, it really is easy to do so if you think about what's happening. So for the next one, um, in an art contest with 10 entries, how many ways can we award first, second, and third? Well, there's an easy way to do this. How many choices are there for the first place? Well, there's 10 entries, so there's 10 choices, right? You can pick if I haven't given anything to anyone yet, there's 10 ways I can select one of the people to be first place. And then there's of course 9 people left to choose to be second place, or 9 entries left, I should say. And then there's 8 entries left to choose for third place. And we don't care who 4th, 5th, 6th, 7th, 8th, 9th, and 10th are, right? There could be a lot of ways of ordering them, but we're not going to worry about that. So this is equal to 10 times 72, which is 720. But another way to think about this is it's equal to 10 factorial divided by 7 factorial. It's 10 factorial because there's 10 factorial ways we can arrange the 10 entries, but then we're dividing by 7 factorial the number of ways we can arrange places 4th through 10th because we don't really care how they're arranged. So another way to write this is as 10 factorial divided by 10 minus 3 factorial. And really what I'm thinking about when I'm doing this is I'm saying, oh, this is exactly 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 7 times 6 times 5 times 4 times 3 times 2 times 1. And of course, the 7 factorial part of both pieces is going to cancel out. So this part here, which is 7 factorial, and this part here, which is 7 factorial, is getting canceled. Now, I don't usually use notation for this formula, but there is notation for this formula, which I never actually remember either, to be perfectly frank. So what this is an example of is the number of permutations, because order matters, of k objects chosen from a group of n objects. And it's equal to, again, this is a notation I typically use, p of n comma k, and it's n factorial, the ways of rearranging the 10 things we have, divided by n minus k factorial, the number of ways you could arrange the leftover things we don't care about. So in this example, there were 10 things we arranged, but then we really didn't care about how we arranged the bottom 7 of them. So we divided by 10 minus 3, which is 7 factorial, to negate or not worry about how those people are getting moved around. But usually I wouldn't do it this way. Like if I was asked this problem, I wouldn't be like, okay, it's 10 factorial divided by 10 minus. No, I'd be like, it's 10 times 9 times 8. Because I know there's 10 choices for first place and 9 for second and 7 for third. Or 8 for third, sorry. So kind of the name of the game for a lot of these problems is to try to think of the problem in the easiest way possible, which is not always easy to do. That's the part that actually takes practice. The math here, the actual calculation part, is usually not that bad. It's more of the figuring out how we calculate it in the first place to do it right. Okay, here's an example I think is very worthwhile. Although it's, again, kind of a pain to write out all the things, but we can do it. Question, yeah.
Like, figure out like fourth, fifth, sixth place, will it change something?
But if we just want to figure out fourth, fifth, and sixth, or if we want to figure out first, second, third, fourth, fifth, and sixth, I know it would be the same answer because we're saying we don't care about who's first, second, and third, and we don't care about who's seventh, eighth, ninth, or 10th. So we care about how those 3 places are out of these 10 people will be exactly the same number, which is 728. Correct. K is the number of things that we care about in the larger number of things that we don't really care about, or that we're choosing a subset from. So let's look at this next example. Yeah. So now we're going to talk about combinations where order does not matter. Or is unimportant. So let's look at this example first. 6A. First, we'll talk about permutations. So how many permutations of 3 letters chosen from the first 5 letters in the alphabet, A, B, C, D, E, are there? Well, we'll write the formula first, just because I think it's worthwhile. Actually, I'm not going to write the formula. I'm not going to write the formula first. I'm going to write the answer first. So I would say my answer is, well, how many choices are there for the first letter? Show me on your fingers. Right, 5. How many for the second one? How many for the third one? How many for the fourth one? Oh, just kidding. There isn't a fourth one. There's only 3 letters, right? So it's 5 times 4 times 3, which is what? 20 times 3, which is 60. Yes, we could have used the formula we just talked about. We could have said, okay, it's 5 factorial divided by 5 minus 2 factorial, which is 5 factorial over 5 minus 3, apologies, factorial, which is 5 factorial over 2 factorial, which is 5 times 4 times 3 times 2 times 1, but the 2 times 1 gets canceled out. So it's exactly also 5 times 4 times 3. No big surprise there. But let's write them out so we can see how the combination part is going to be different. And you might not want to write all this out, but I'm going to. Maybe not all of it. So we could have A, B, and C. But since we're talking permutations, order matters. And there's going to be 6 different ways of rewriting these same 3 letters in different orders. A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. And then for any other 3-letter combination, there's going to be 6 different ways of permuting those 3 letters. So for A, B, and D, there's also going to be 5 other ways of writing that. ADB, BAD, BDA, DAB, DBA. We're not going to write them down though. And then so let's write down all the other ways we can find 3 letters. So you get A, B, and E. And I've exhausted A, B with another letter. So now let's do A, C, and D, A, C, and E. I've exhausted A, C and another letter. So let's do A, D, and E. That's all the different letters we can have with A. Now we'll move on to B, C, and D, B, C, and E. I think that's it for B, C. And finally, C, D, and E. I always miss one. B, C, D, B, C, E, B, D, E. I miss B, D, E. Smooth. I don't know how I missed that one. And B, D, E. So each of these would have 5 other orderings for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 6 is 60 different permutations. But then we can also very easily see the answer to the next question, which is how many combinations of 3 letters are there chosen from A, B, C, D, E? Well, there's 10. A, B, C, A, B, D, A, B, E, A, C, D, A, C, E, A, D, E, B, C, D, B, C, E, C, D, B, D, E. And I don't care if I write A, B, C or C, A, B or A, B, D or B, A, D or whatever the way I'm going to write it. There's only one way of or one combination that's those first 3 letters, A, B, and C, no matter which way you permute them. So the answer to the next question is 10, but it's 10 because we've taken the number of permutations, the permutations of 3 things from 5 things, and divided it by the number of ways of permuting the 3 things we've chosen, right? We don't want to overcount by a multiple of 6. So we're going to divide by 3 factorial. And this is correct. That's going to end up being 5 factorial over 5 minus 3 factorial, and also divided by 3 factorial. Let's write it out. That's 5 times 4 times 3 times 2 times 1 divided by 5 minus 3 is 2 times 1. 3 factorial is 3 times 2 times 1. The 3 times 2 times 1 cancels, and we get 20 divided by 2, which is 10. So typically, the way to think about the number of combinations is you take the number of permutations, but then you divide by the number of ways you can permute the things that you've chosen. Yes. This formula has a much nicer notation, in my opinion. This is called, so yeah, let me just write it out. Let me start off with another page here instead of trying to fit this at the bottom here. So formula for the number of combinations, not permutations, combinations, where order doesn't matter, of k objects chosen from n objects is, there's notation like the C of n comma k, but my preferred notation and any person who teaches math's preferred notation is probably this notation. A big parentheses with an n over a k, but there's no like fraction line. You don't say n divided by k or n over k. You just say the way you say this, the correct way is to say n choose k. That is the way we read this. And it's exactly equal to n factorial divided by n minus k factorial and k factorial. And if you like, it is okay to think of it as the number of permutations divided by k factorial, the number of ways of ordering the k things we cared about. This number, in my opinion, is super cool. This number you have seen a lot already in your mathematical life, because this is also known as the binomial coefficient. So if you've ever multiplied out, like say x plus 2 to the 3rd power, or something like x plus h to the 5th power when you're doing the limit definition of the derivative way back when, these numbers are the numbers that are the coefficients of each of the terms. These are the numbers that show up in Pascal's triangle. if you start writing out the numbers in Pascal's triangle, which is my favorite triangle, that's one of my favorites. I mean, I got lots of favorite triangles. Those numbers there, this first row is kind of lame, but this next row, that's 1 choose 0 and 1 choose 1. This next row is 2 choose 0 and 2 choose 1 and 2 choose 2, and so on and so forth. This is 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Again, 3 choose 2, meaning the number of ways you can pick 2 things out of 3 things without caring about the order of those things. So there's something else I want to say here. Oh, so what I'll point out here is actually this is where that thing I said about 0 factorial needing to be true needs to be true. So if I said, talk about our hands for a second. Got 5 fingers. What's 5 choose 1? Well, it's the number of ways I can pick 1 finger out of 5. So there's 1, 2, 3, 4, 5 ways I can do that, which totally makes sense, right? It's 5 factorial over 5 minus 1, which is 4 factorial times 1 factorial. And that's going to be 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times another 1. And yes, everything cancels except for the 5 over 1, which is 5. Here's an interesting point that I think is, well, here's the point I think is interesting. It's also the same as 5 choose 4. The number of ways of picking 1 finger is the same as the number of ways of picking 4 fingers, because instead of picking 4 fingers, I'm really thinking about picking the 1 finger I'm not going to pick. I'm not picking my thumb. I'm not picking this one. I'm not picking that one. I'm not picking that one. I'm not picking that one. Oh, that's the number of ways I can pick 4 fingers is by picking the one I'm not picking. So this is also equal to 5 choose 4. So one thing that's nice about this choose function is there's symmetry. If you have something choose a number, it's the same as something choose the difference between those two numbers. So for example, 10 choose 8 is the same as 10 choose 2. Look at it. 10 choose 8 is going to be 10 factorial over 10 minus 8 factorial times 8 factorial. And 10 choose 2 is going to be 10 factorial over 10 minus 2 factorial times 2 factorial. Those are the same thing. That's 10 factorial over 2 factorial times 8 factorial. That's 10 factorial over 8 factorial times 2 factorial. They're the same. So we have this nice symmetry property for the choose function, which is that n choose k is equal to n choose n minus k. All right, here's the other thing I wanted to point out. Okay, back to my fingers. How many ways can I pick all 5 of them? 1. I pick all 5 of them. That's it. Okay, so what that means is that 5 choose 5 should equal 1. Watch. So I'm going to 5 factorial over 5 minus 5 factorial times 5 factorial. So that's going to be 5 factorial over 0 factorial times 5 factorial. The 5 factorials cancel, right? 5 times 4 times 2 divided by 5 times 4 times 1. So I'm going to get 1 over 0 factorial, but we just said that had to equal 1, which means, oh yeah, we definitely need 0 factorial to be equal to 1. Otherwise, the math doesn't work for this formula. So that's why 0 factorial, or it's one of the reasons why 0 factorial is defined to be equal to 1, because otherwise this formula doesn't work the way it's supposed to. Okay, here's another thing that's a little bit disappointing, or at least feels weird to wrap your head around, I feel like. What's 5 choose 0? How many ways can I pick 0 of my fingers? 1 way. I pick none of them. Or another way is how many ways can I not pick all of my fingers? Well, there's one way to pick all of my fingers, so there's one way to not pick all of my fingers. I exclude them all. It's not a great example when I'm talking about fingers. There's a better example we'll talk about in just a second. So 520, though, because of the symmetry here, is also going to be 1. It's going to be 5 factorial over 5 minus 0 factorial times 0 factorial. The 5 factorials cancel out. We're left with 1 over 0 factorial, which is 1. Sure. Yeah. A better example of this is coin flips. So let's say that we flip four coins. Flip four coins. How many ways can we get X number of heads? Where X could be equal to, well, what's the least number of heads we could get? 0, right? You get all tails. Oh, getting none of a thing is like getting all of the other thing. So we can get X equal to 0 or 1 or 2 or 3 or 4. So let's look at this here. And then we're going to kind of make a connection. So I'm actually going to write these all out. So 0 heads means 4 tails. Well, there's only one way to get all tails. Every coin flip was a tail. You can either think of this as taking one coin and flipping it 4 times, or flipping 4 coins at once. If you do it 4 coins at once, which I think is the better way, I like to imagine all the coins are painted different colors. So that, oh yeah, when the blue one is heads and the red one is tails is different than when the blue one is tails and the red one is heads. Or at least we have to count them as different. So then if I want one head, well, it's going to be either heads first and 3 tails, or tails then heads then tails tails, or tails tails heads tails, or tails 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 heads. For 2 heads, there's going to be 6 ways of doing this. We're going to have heads heads tails tails, heads tails heads tails, heads tails tails heads. Sure. Tails heads heads tails, tails heads tails heads, and tails tails heads heads. And then for the other 2, it's actually going to be very much the same as the first 2. 3 heads is like having 3 tails. We're just going to interchange the heads and the tails. So we're going to get tails, heads, 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 tails, heads, 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 tails, heads, and then heads, 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 tails. And finally, 4 heads, well, there's only one way. Heads, 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 heads. Now here's what I want you to know. These are exactly the numbers you would get if you just said, oh, that's 4 choose 0. There's exactly one way of getting 0 heads. This is going to be 4 choose 1, which is equal to 4. There's exactly 4 ways of getting 1 head and 3 tails. This is going to be 4 choose 2, which is equal to 6. This is 4 choose 3, which is equal to 4. This is 4 choose 1, which is equal to 1. Oh my gosh. And I will point out those are the numbers in one of those rows of Pascal's triangle, 1, 4, 6, 4, 1, which are also the coefficients if you multiply out x plus h to the 4th power, right? X plus h to the 4th power is 1x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus 1h to the 4th. So it's kind of useful. But these numbers do come up a lot. They are the binomial coefficients. They're also called the choose function. And again, it's the number of ways you can choose a things out of n things, where order doesn't matter. So we go back to our example of the art entries, and we have, say, how many ways can we pick? Now, instead of picking first, second, and third, we're just going to pick a top 3. Top 3 from 10 entries. And we just say each of the 3 is a winner. Not first, second, and third, just winner, winner, winner. Well, that's going to be 10 choose 3, which is going to be 10 factorial over 10. So I keep writing 10 minus 3, but I really just like to think of it as, okay, I know I'm going to get a 3 factorial down there and the difference between 10 and 3, which is 7 factorial. If I ignore the factorials in this choose function, the bottom thing should add up to the top thing. They don't really, like 7 factorial plus 3 factorial does not equal 10 factorial, but 7 plus 3 equals 10. That's what I'm looking at when I write this. And then I'm going to write this out as 10 times 9 times 8 times, I don't really want to write the rest. Instead of writing 7, 6, 5, 4, 3, 2, 1, I'm going to write 7 factorial. And on the bottom, I have my 7 factorial, which I'm writing second now, and 3 factorial is 3 times 2 times 1. Those get to cancel, so I'm left with 10 times 9 times 8 divided by 6, so 10 times 9 times 8 divided by 3 times 2 times 1. 10 over 2 is 5, 9 over 3 is 3, and I get 5 times 3 times 8, which is 120. So there's a lot fewer ways, right? When we cared about who was first, who was second, who was third, there was 720. And I know my time is up, so I should stop talking. That's it. So again, almost always, if you're talking about combinations versus permutations, there should be more permutations if everything else is the same versus the number of combinations. All right. Yeah, so I'll try to get a practice exam for Varn written and posted before class on Wednesday. Depending on how you're all, so you'll have tests on Friday. Lee's class is before class on Friday and Varn's class is after class on Friday. Okay. So I guess on Wednesday we could probably try to do some exam review. And then on Friday, I don't know, we should probably talk about more content on Friday because it's kind of silly to do an exam review for people that have already taken an exam. So yeah, we'll probably move on to talking about probability on Friday, which should not be covered on your first exam. On this exam, sorry. All right. I'll see you all later. And also, I will not be in drop-in right now from 1 to 4. I have a thing I have to go do. So you should still go there if you're looking for help with math. Don't expect to see me there today.